Everyone to today's webinar presentation. My name is Arie Hakimian, an application scientist here at C-Therm. But today I want to welcome our guest speaker, Christian Bykovets, who is from Evonik and talking about fumed alumina, maintaining thermal conductivity of silicones while functioning as a suspension aid. So this is going to be a very application-focused webinar here today. And I'll be turning it over to Christian in just a few moments. But before that, just wanted to do a little bit of a quick introduction, folks that may be new to C-Therm, a little bit of a background about who we are and what we do. So C-Therm Technologies, we are experts in thermal conductivity, specifically the transient class of measurement technique. Really, our purpose is to simplify thermal conductivity testing for the materials of tomorrow. And again, this is done through the advancement of some of the most prominent transient techniques, which are available on our core instrument platform, Trident. So Trident, you can see here, is a modular system. It brings together 4 different options for thermal conductivity. And really, depending on the type of samples that you're testing, the conditions you're looking to measure under, these will all dictate which method is most appropriate. But the idea behind Trident, again, having this flexibility, really centers from this quote from Abraham Maslow. It's one we like to reference. When all you have is a hammer, everything looks like a nail. So the idea here is one of the biggest sources of poor data we see out there is taking a good method of measurement, but just applying it on a sample or a scenario it wasn't designed for. So again, with Trident, kind of gives you that flexibility to pick and choose the best tool for the task at hand. Regardless of where your knowledge is on thermal conductivity, this is a really great resource I'd recommend checking out if you haven't already done so. It's our updated method selection guide for thermal conductivity. Really covers all the methods that we have available on Trident, as well as other prominent methods available in industry, including steady state options, and some of the more novel optical or frequency-based testing capabilities as well. Really good resource, whether you're just starting out in thermal conductivity or kind of just trying to get a quick refresher on what the options exist in the market. So again, this is available as a free resource download. Definitely feel free to check that out. But all that being said, that kind of brings me to the end of my quick little intro here. Again, at this point, I really want to turn it over to our guest here today, Christian. So I'll invite you on screen here to take us through your content. Thank you for joining us here today.
Thank you, Aria. Good afternoon, everybody. As Aria said, my name is Christian Bykovets. I work for Evonik Corporation over here in the Americas as an applied technology scientist, focusing mainly on our fumed metal oxide materials. Today, specifically, we will be talking about fumed alumina, our AEROXIDE name brand of materials. Its use as a suspension aid and highly filled thermally conductive silicone adhesives and sealants. Give me one moment to share my screen. Make sure. Are we seeing the screen on our end? I'm sorry, I'm not familiar with Zoom too.
Nothing yet there, but
nothing yet.
I'll let you know when the code shows up.
Okay, there we go, I believe.
Yeah, perfect.
Okay, let me just get to my presenter view. Okay, so again, we'll be talking about our AEROXIDE materials, our fumed metal oxides, our fumed aluminum oxide specifically as anti-settling agents for thermally conductive silicone compounds. First, a bit about the EV market as it stands today, how Evonik plays a role in the EV market. Today's trends in EV are focused on improving safety, distance, charging efficiency, and lowering the weight of the vehicle. Our Smart Effects business line, which is the business line I work for our fumed metal oxides, we support these goals with our raw material technologies in support of new developments in these target areas. We are established in the battery cell industry with products supporting cathode, anode, and separator coatings, and now we are emphasizing the battery pack optimizations to improve thermal conductivity and thermal insulation while improving performance. First, we want to take a look at the value pyramid of existing thermally conductive fillers that are commonly employed from highest price performance to lowest. On the high end, we have boron nitride, aluminum nitride, and hybrid powders of the two using fine aluminum oxide as well. While these are highly efficient in the category of thermally conductive materials, oftentimes these are too costly and provide higher performance than is necessary for many applications. While at the low end of the pyramid, we have aluminum oxide created as a result of the Bayer process. And while this product is quite lower in cost, it is the least efficient option in terms of thermal conductivity. So here we want to focus on the middle of the value pyramid and the use of spherical alumina specifically. This is a commonly employed choice for thermally conductive adhesives. It provides the greatest combination of cost and performance benefits. And while moderately efficient in terms of thermal conductivity, it does have some slight drawbacks. These are typically a large particle size material, which tends to lead to settling of the spherical alumina when highly loaded in these adhesive systems when used at the high concentrations needed to generate thermal conductivity. Again, this will lead to syneresis and typically poor shelf life over time of the final product. So I'd like to talk to you about the solution we have for these issues here at Evonik. Helps to prevent the settling of the large spherical alumina particles without having a negative impact on thermal conductivity of the system overall. And that solution, again, is fumed alumina, which works to fill the voids between the spherical alumina particles and functions as a suspension control additive. First, a bit about the production process of fumed alumina. Now, while you might hear the name alumina and think this is technically a metal, there is no ore involved. It is a totally synthetic process, starting with aluminum chloride, which does originate as a metal, but is purified into a silane by some of our colleagues on the silane side of the business. The fumed alumina is produced in a flame hydrolysis process, much similar to fumed silica, which is another big material that Evonik uses for our fumed metal oxides. Relies on oxygen and hydrogen as reactants. However, whereas fumed silica production uses silicon tetrachloride, again, the fumed alumina production uses aluminum chloride. Hydrogen and oxygen are reacted in the presence of the aluminum chloride. Water is formed via the oxyhydrogen reaction, which then reacts with gaseous state aluminum chloride to produce the desired alumina and an HCl byproduct. Once the product is cooled, a deacidification step is performed to clean the solid state aluminum of HCl. The hotter areas of the flame tube, liquid state droplets of the alumina collide and merge together to form larger and larger droplets. Cooler areas of the tube, they partially solidify now while continuing to collide, coalescing into aggregates made up of primary particles that are essentially sintered together due to the high temperature of this process. At even cooler areas of the tube, the aggregates will continue to collide, but now being in a fully solid state, they no longer coalesce into aggregates. They collide and are held together by weak interaction forces, forming the agglomerates that are found in the final packaged material that you may or may not be working with. The agglomerates can be sheared and processed for dispersion to break up the size of the agglomerates, but can never undergo enough energy to actually undo the sintering process I spoke of and reduce the aggregates to primary particles. So when we talk about fumed metal oxides, including fumed alumina, we typically don't refer to the materials by their primary particle size because this is really a theoretical value. We typically refer to the aggregate size of the material. We'll discuss this a little more in a few slides. The process is further controlled by varying the concentration of reactants, flame temperature, and dwell time in the hydrolysis tube to modify particle size, distribution, and surface area. Overall, the fumed alumina purity is very similar to the fumed silica purity. It comes in at about 99.8% pure alumina. Again, much like fumed silica, fumed alumina does not exist as individual nanoparticles, as I said, but rather groupings of nanoparticles that are permanently sintered together in this process to create the aggregates. And as I just mentioned, fumed alumina does have aggregates on the nanometer scale, which allows for greater particle packing and filling in the gaps between much larger spherical alumina particles. This supports better transfer of heat through the system overall, as you can see here, and maintains the overall thermal conductivity of the system, which we'll discuss in a few slides. The main point, however, is the anti-sedimentation properties of the materials at these high loading levels of spherical alumina, for which the fumed alumina serves as a suspension aid. The addition of AEROXIDE fumed alumina materials creates a matrix through hydrogen bonding interactions that serves to present the phase separations that these highly loaded materials are typically subject to, focusing on two commercial grades that will continue to come up in this presentation a bit, the AluC 805 and the VP Alu 45RK, two hydrophobic materials used for these purposes. Recommended addition levels for the silicone materials would be around 1 to 2% of either of these grades for the anti-sedimentation purposes, but we'll discuss that a little more later in the presentation. First, we want to look at the impact of viscosity on the silicone compounds of these fumed alumina materials. And the information you're seeing here shows the difference of viscosity of these materials in a vinyl silicone, specifically as a factor of concentration and specific surface area measured by BET analysis. Fumed alumina in this respect performs similar to fumed silica in that the thixotropic effects of these materials is reduced with a lower specific surface area, here indicated by the grade nomenclature. So Alu 130, for example, would have a specific surface area of 130 meters squared per gram. Alu 65 would be 65 meters squared per gram, so on and so forth. The AluC and the AluC 805, C being the Roman numeral for 100, would be a specific surface area of 100 meters squared per gram, just to explain that nomenclature there. The two VP products we have highlighted, the 45 and the 45RK, were developed to reduce viscosity at higher concentrations. As you can see here, the VP Alu 45RK is loaded very highly, as is the 45 itself, the hydrophilic version. Get much higher loading levels with less viscosity impact with both of these materials. As I said, the Alu 45 does not serve to reduce the viscosity quite as much as the RK, which is the hydrophobically treated option. There's a reason for this. This is due to the similar nonpolar nature between the hydrophobic treatment of the RK product and the vinyl silicone used in the study. The similar polarities between these two materials allows for greater resin interaction with the fumed alumina, which serves to partially inhibit the van der Waals interactions between alumina agglomerates that serves to help generate viscosity in the system, allowing for higher loading levels of the material with less upwards viscosity impact. The same principle applies in explaining the viscosity differences between the other hydrophobic grades here. Again, the AluC, the hydrophilic version, and the AluC 805, the hydrophobic version. Again, the same principles would apply due to the similar polarities between the silicone and the hydrophobic treatment. You're able to get a higher loading level with less viscosity impact, as the fumed alumina is not generating and interacting with itself enough to generate efficient viscosities in these systems. So to look at how we measure viscosity, we rely on a rheological measurement known as the 3ITT, which is a 3-interval thixotropy test. The test begins at low shear conditions, typically, at least in this case, 0.1 reciprocal seconds of shear rate to establish a baseline viscosity of the formulated product. From there, the rate of shear increases to create a high shear condition, in this case, 50 reciprocal seconds, to evaluate parameters such as the shear thinning behavior of the material and the lowest viscosity possible for the product while undergoing these intense shear conditions. From here, the shear rate returns to the baseline measurement parameter, again, 0.1 reciprocal seconds, to evaluate the post-shear recovery of the material, how much the viscosity will recover once the high shear condition has been removed. The left images here, that gives you a correlation between the typical viscoelastic behavior in relation to the shear rate during the evaluation. So you can see On the left, where you see the shear rate axis, you begin at a very low shear rate, go up to a very high shear rate, and back down to low. And below that, in terms of viscosity, you can see the viscoelastic behavior of the materials. It'll establish a baseline. It'll shear thin under the high shear conditions typically, and then will exhibit some degree of post-shear recovery when exposed to the low shear conditions following the high shear rate testing. The images to the right show the practical application of this testing, evaluating one sample of fumed alumina versus various fumed silica grades. Here with the 2% VP-Alu45RK, the topmost image, we observe a distinct thixotropic nature of the product at rest. You can see here it has a viscosity of about 100 Pascal seconds at the low shear rate condition. Then we see a significant shear thinning behavior following the distinct thixotropy, the gray area in the middle of the graph. You can see the viscosity is thinned quite a bit at that high shear conditions, and a bit of a slow structure recovery here, but there is a degree of post-shear recovery following that high shear condition when it is returned back to low shear conditions. If we look at the two fumed silica grades below, the aerosol R202 and the aerosol R805, both used at 0.1%. Again, these were used a bit lower as they are much more efficient at thickening in these systems in this particular grade of fumed alumina. So to generally keep a relatively similar baseline viscosity, a much lower concentration of silica was used here. But essentially the opposite behavior is found when we look at these silicas. At rest, we observe a very low thixotropy of the material in both cases, with only marginal room for shear thinning behavior, as it is so low in viscosity to begin with and close to the base viscosity of the polymer. However, as the higher shear conditions essentially work to redistribute the silica throughout the system, we see an initially high post-shear recovery with viscosity decreasing over time. Due to the overall inefficient thickening of silica used at such low concentrations. Again, if you were to use fumed silica typically for a thickening purpose, for rheological purposes, you would use a much higher concentration here, perhaps 1% up to, let's say, 5%, again, to keep the baseline measurements relatively similar between the fumed alumina and the silica. As a much lower concentration was used in this particular study. So to move on to some of our our anti-settling materials and our thermally conductive testing that we prepared for you here today. To outline some of those methods, some of the materials you will see will be either 70% of the active particles or 80% of the active particles. By active particles here, we mean the spherical alumina. Both a 40 micron and 2 micron spherical alumina were employed in these tests. Used at either a ratio of 60 40 in favor of the 40 micron spherical alumina, or only the 40 micron was used and not the 2 in some instances as well. This is a vinyl terminated PDMS. Again, this was the polymer of choice for all of the testing we completed here. We do recommend dry mixing of the fillers, basically meaning to mix the spherical alumina and the fumed alumina together by itself. This was done here in a speed mixer, 3 rounds at 60 seconds at 2000 RPM, just to homogenize the fillers themselves and make sure they have good interaction and are able to work very synergistically in the material. To make the compound itself, the fully formulated compounds, again, was done in a speed mixer, 4 rounds at 60 seconds to complete the entire mix, again at 2000 RPM. A sample of 6 millimeter thickness was used for the thermal conductivity measurements. If you look to the images below, the first image from the right is basically what we're referring to. It's this little, we'll call it a puck of material of the cured silicone on a 6 millimeter thickness to measure thermal conductivity of both sides of the material to evaluate anti-settling. We'll take a look at that in a bit. And of course, the C-Therm instrumentation was used for all these surface thermal conductivity measurements we employed during the course of this evaluation. So here we evaluate the anti-settling effects of fumed alumina in these highly filled vinyl silicone systems. Here it was just employing the 40 micron spherical alumina by itself as the main thermally conductive filler. This was not using a blend, and this was with a 200 centipoise vinyl silicone material. The test is fairly straightforward. You can see it there on the right. Basically, a syringe was loaded with the fully formulated silicone compound, left to sit on the shelf, basically a shelf life test, and ultimately measure how many milliliters of fluid were present at the top of the syringe following any instances of syneresis. What is shown here is the specific concentration of spherical alumina plus 2% fumed alumina for anti-settling purposes. If we look at the left topmost graphic for 70% spherical alumina, and again, 2% fumed alumina added here, we see that with 70% spherical alumina, due to a lower volume fraction of solids and an overall lower viscosity, the material in general is more prone to settling and syneresis. As you can see, they all tend to show some degree of phase separation over a 72-hour period. With that being said, there is still a considerable benefit observed versus the blank material containing no fumed alumina, specifically with the hydrophobically treated VP Alu-45 and the VP Alu-45 RK. The RK here being the dotted line on the left. You can see the greatest suspension benefits realized with that hydrophobically treated material. And we see that, yes, so for the 45 RK, we do get greater benefits at the 70% as well as the 80%, which we'll take a look at now. For the 80% concentration material, we see a much different situation with some samples exhibiting no degree of phase separation over a 72-hour period. Again, the hydrophobic VP Alu-45 RK, along with several higher surface area options in this instance, completely prevents separation during the duration of the test at the 80% concentration of spherical alumina. Only the very low surface area VP Alu-45, which is again is hydrophilically treated, does not entirely prevent separation here. Lastly here, if we look to the right of the 80% graph, we see high and low shear viscosity of the materials. Most noticeably, the similar viscosity of the 45 meters squared per gram materials to the blank containing only spherical alumina. With the higher BET materials, you tend to get better separation control from modifying the overall viscosity, but the benefits of the VP Alu-45 RK hydrophobic treatment are again seen by creating separation control in the system while maintaining a low workable viscosity. And here you have on the left, you have the legend of the samples themselves from the blank down to the Alu-C805, and to the right of them obviously corresponds the viscosity values at both a low and high shear value. And again, you can see the benefits of the VP Alu-45 RK maintains a workable viscosity here, pretty mid-range across the course of the evaluation of the blank and the 4 fumed aluminas. But of course, it does give a very high degree of suspension control in the 80% spherical alumina sample. Here we look at a comparison of 2 spherical alumina blanks, essentially one at an 86% loading of spherical alumina and another at 88% loading. The 88% is the plus 2% blend here, second from the left. So that was the original 86% blend. Again, here we're using the 60-40 ratio of 40 micron to 2 micron, still in the 200 centipoise vinyl silicone. So the blend is the 86% of that ratio, and then plus 2% is the 88% loading of that ratio. We have 2 fumed silica employing systems to the right of that, and 2 fumed alumina employing systems toward the end of the graph. Again, focusing on viscosity generation in the vinyl silicone system, as well as thermal conductivity, as what we were looking at here. But to first look at viscosity, we will look at the fumed silica, the 2 samples in the middle, the R805 and the R202. Note the considerably higher viscosity in this system versus the spherical alumina blanks and even the fumed alumina containing samples. While the spherical alumina blanks and even while this result is expected, due to the higher surface area of both of these fumed silica materials than the aluminas, and shows a rheological performance that is typically what you would want to see when using fumed silica. It is not necessarily a benefit to these systems, where low viscosities are typically beneficial for processing and application purposes. Perhaps more importantly, the fumed silica actually has a deleterious effect on the overall thermal conductivity of the system. As you can see there by the bar graphs, they are quite significantly lower than the 88% blend of material, which is obviously not what you want to see in these highly thermally conductive systems, and only somewhat on par with the 86% blank with the lower concentration of the spherical alumina. However, when we evaluate the fumed alumina samples, we first notice a much more manageable viscosity, a much lower viscosity, as you can see here, than the fumed silica materials at equivalent loading levels. Again, all this was done at plus 2%, again, owing to the much lower specific surface area here versus the chosen fumed silica materials. More importantly, however, is the overall thermal conductivity of the fumed alumina containing samples versus both the fumed silica samples and the blank samples as well. The alumina in general has a much greater thermal conductivity than the silica, explaining the differences between the thermal conductivity values between the silica and the fumed alumina samples. But the highlight here is versus the blank samples, the 86 and 88% samples. Because alumina in general is high in thermal conductivity, the use of the fumed alumina allows for maintaining the thermal conductivity of the system is very much on par with the blank at 88% loading, as both the blank and fumed alumina samples now both contain 88% of alumina fillers. It's important to note that while fumed alumina is not meant to be a replacement for spherical alumina, you will not be able to load fumed alumina highly enough on its own to generate a similar thermal conductivity values while maintaining a workable viscosity. The benefit is that it will maintain the overall thermal conductivity of the system, despite its use in conjunction with the anti-sedimentation benefits we've seen on the last slide. So again, the purpose here is really to maintain that thermal conductivity while functioning as a suspension control agent. Due to the surface area of these materials, their highly rheological nature, you'd never be able to really use the fumed alumina as a one-to-one replacement of the spherical alumina. You would never be able to say, load the fumed aluminas at 86% or so and maintain and achieve the same thermal conductivity. You'll likely achieve the same thermal conductivity, but your viscosity will be completely impossible to work with due to the rheological nature of these materials. So again, the benefit is really the suspension control in conjunction with maintaining the workable viscosity and the thermal conductivity of the system. Finally, we look at both thermal conductivity of the vinyl silicone material in conjunction with the anti-sedimentation properties previously described. Here again, we cured a 6 millimeter disc. You could see it on the left of vinyl silicone filled with 80% of the 40 micron spherical alumina. Again, this was our blank sample, and these were alongside test samples of 80% spherical alumina with an added 2% of a variety of our fumed alumina grades here, the VP Alu45 and 45RK, as well as the Alu130 and Alu-C805. Firstly, to look at viscosity, we again see the same trend related to higher overall viscosity of the material as a function of increasing specific surface areas. So here you'll see, of course, the higher surface area materials, the Alu-C being 100 meters squared per gram and the Alu-130 being 130 meters squared per gram, of course, give the highest viscosity. Again, as the 45s have a much lower specific surface area and are basically created to maintain a low viscosity of the system. They're much more on par with the blank, the spherical alumina only sample without any fumed alumina added. They have very similar viscosities here. But in terms of anti-settling in this evaluation, we no longer look at the settling of the material over the storage life of the uncured silicone, but we now look at the settling of the material post-application and during the curing process as a function of thermal conductivity. Again, to do so, we cured the 6 millimeter disc and using the C-Therm thermal conductivity measuring unit pictured here to the right, measured the thermal conductivity of both sides of the disc after full cure. Looking at the 80% blank here labeled as no additive all the way to the left, we observe a high thermal conductivity on the bottom side of the disk and a very low thermal conductivity of the top side of the disk. And you may be wondering why this is. And of course, that is because without any sedimentation preventative additive, the spherical alumina settles out of the silicone compound so quickly that before the material is actually entirely cured, the spherical alumina has essentially all settled to the bottom of the disk, which creates an inconsistent thermal conductivity throughout the system. When we look at the fumed alumina containing samples used here again at 2% concentration, we see a much more consistent thermal conductivity across both sides of the disk, showing that the high rate of settling of the spherical alumina blank has largely been controlled by the addition of fumed alumina, resulting in a much more homogeneous cured silicone compound post application. So I really think this is one of the definitive slides if you have to take something away here. We've seen the anti-sedimentation benefits. Again, you're seeing them here showcased pretty well in terms of maintaining that thermal conductivity across the entire surface of the cured adhesive rather than just having that settling and having a weak thermal conductivity on one side. And again, this all allows the fumed alumina, even this 2% addition low loading level gives you those suspension benefits while in most cases maintaining a very workable viscosity for your thermally conductive silicone compound. So again, to focus on some of the advantages of the fumed alumina materials, the special aggregate structure of the AEROXIDE fumed aluminas, which I described a bit before, does work to prevent the settling of the main thermally conductive fillers, such as spherical aluminum oxides, typically 5 to 100 microns in particle size. Here today, it was typically 40 microns in particle size, and typically require a high loading of 80% or greater to achieve sufficient thermal conductivity values of the final material. Even in the event of settling, should you experience settling in your final compound, redispersibility is improved by addition of the AEROXIDE fumed alumina, meaning it would be easier if you did need to remix or reagitate the material to some degree. It should be a bit of an easier process to reincorporate and redistribute the spherical alumina as well as the fumed alumina when used in conjunction together in your final silicone compound to really rehomogenize everything in an efficient way if needed. But to hit on some key points here, dry mixing of the fillers is recommended. Again, if you're going to use the fumed alumina as a suspension aid, you should always be mixing it with the spherical alumina itself, just in a dry mix process to really integrate those materials together and allow them to work synergistically in the final product. AEROXIDE alu products have almost no impact on thermal conductivity in comparison to fumed silica. Again, they don't necessarily boost the thermal conductivity of the material, but when viewed against fumed silica, which detracts from the thermal conductivity, your fumed alumina will actually allow you to maintain the same thermal conductivity, will not detract at all, and will allow you to have a very stable thermal conductivity because of those anti-sedimentation properties. The lower surface area products have a lower impact on viscosity increase than higher surface area products. I touched on that quite a bit. Has to do with the specific surface area of the materials and their ability to efficiently thicken the materials, which again was the purpose for the 45 and 45 RK to maintain a low workable viscosity, really was the inception or the reason for the inception of those products. And the hydrophobicity, again, this is why we focus on the ALU-C805 and the ALU-45RK. Hydrophobicity seems to be an advantage at low shear rates for anti-settling properties. It may slightly decrease the thermal conductivity. We didn't see that too much here today at 2% loading levels. It's possible if you were to go higher than 2%, you may see a bit of a drawback, again, but only slight and not nearly to the degree that the fumed silica, again, would detract from thermal conductivity in these studies. And again, to hit on the recommendation, for both of these grades, you would want an addition of around 1 to 2%, maybe a little higher, 1.5 to 2% for the VP ALU-45RK, but 1 to 2% of the ALU-C805. Generally, if you're using any of these fumed alumina grades for their anti-sedimentation purposes in these applications, 2% is generally a very good starting point for either the hydrophobic or the hydrophilic grades here that we've discussed a bit today. Just to give some technical specifications here to show you the specific surface area, bulk density, so on and so forth for some of the grades we talked about here today. Here we have the ALU65, the ALUC, ALU130, and ALUC 805, just to give you some technical data on them. But to kind of end with discussing the benefits of our fumed alumina product portfolio, the hydrophilic and the hydrophobic materials for their use in these applications. It's generally more cost efficient than some other options you may have, such as graphene, copper, so on and so forth, to prepare thermal conductivity compounds. So it's a better price performance ratio in terms of the benefits you get from using it, the cost versus some of those other options. Um, Alumina, as of course, an insulator, does not conduct electricity, so it's not going to add any electrical conductivity to the material, which obviously for EVs would be quite detrimental. They'll all be electrically insulative when using the fumed alumina. Um, it is it can improve your rheological properties again if that was something you needed. You needed to boost your viscosity to some degree. Of course, you would select based on the specific surface area of the fumed aluminas to do so. But again, we have a wide product portfolio, so a range of thickening behavior can be realized depending on the grade selection. And it's chemically stable and non-reactive, of course. It will not degrade or oxidize with any of the organic compounds used in the thermally conductive compounds themselves. So again, really the takeaway I want everyone to have today is the fumed alumina is used not to necessarily increase your thermal conductivity, but to maintain your thermal conductivity of these highly filled systems while preventing the sedimentation of the thermally conductive fillers over time and allowing you to have a workable viscosity in your final product, as well as a final product once applied that has a very consistent thermal conductivity across the entire surface area of that material. And with that, I believe that brings me to the end of the presentation.
Perfect. Thank you very much, Christian, for taking us through that content. So for the folks on the line here, I'm just going to go into a quick outro to wrap things up here today. Again, if there was any questions, if you had anything you wanted to speak with us about, you can post that into the Q&A, and we will take a look at that shortly. Um, just going to... There you go. Perfect. So yes, just to wrap things up here today, just going to bring these slides up on screen. So folks, if this type of content was of interest, we do have quite a library of past resources, both webinars as well as some tech library content. So some of the data or papers featured in some past presentations, you can find that all on our website. Um, excuse me. Just wanted to put in a little plug for our final webinar of 2025, which is coming up on December 16th. We will be having a guest speaker join to talk about advanced composites, key enabler in next generation electronics. So again, if you guys are interested in kind of sticking with some of the final content here that we'll be putting out before the holiday break, definitely feel free to register for that. For folks that may have interest in a broader range of material characterization, kind of mentioned at the beginning, but we are partnered with both Rigaku and Metrovid for their line of thermal analysis and mechanical analysis testing equipment, respectively, for North America. If you have interest or needs outside of thermal conductivity testing, these are certainly areas we are happy to support. And our thermal analysis labs group is our contract testing division here at C-Therm. So if you were looking for a group to assist with some testing needs, not necessarily bringing something in-house, again, feel free to kind of mention that in a comment or reach out. We'd certainly happy to direct you to the appropriate resources. Um, In the context of kind of next steps, if folks are interested in any of the additional measurement capabilities or testing services, we're more than happy to schedule a free technical consultation, maybe meet with you one-on-one, learn a little bit more about specifically what you're trying to do, and provide some recommendations. We do this quite regularly. We can kind of course, schedule this for a time that works for you. But also, if you're just looking for some budgetary information, you like what you see, it's something you would looking to kind of assess from maybe there's some uh, funds lying around here before the end of the year or something you're looking to budget for here in 2026. We can certainly provide that information accordingly. And kind of looking through the list of the registrants for those that are in the academic sector, I will just make a note of our academic support program. Kind of see some of the benefits here listed on screen, discounts, and some benefits on some of the warranty maintenance packages and others. So if you are reaching out to us and with an interest in bringing an instrument in-house, and you are from an academic institution, please make a note of that, and we're certainly happy to apply this discount on your costing. Lastly, I will just ask for those that are looking to keep up to date with us. Everything that we do is posted first on LinkedIn. So this is everything from blog pieces, content, upcoming webinars, whatever that may be. So if you're not already doing so, please give us a follow on LinkedIn if you're looking to stay up to date.